we are going to study the steady-state relationship of a synchronous machine. Now we focus on the round rotor machine. Now this slide shows the terminal voltage for a round rotor motor. So here the equation is basically for phase A voltage, V sub A, it is equal to d lambda A dt, then plus the voltage drop on the resistance. Because for the machine, you always have the winding resistance on the phase A winding. So that's R sub S. So that means this VA is equal to R sub S IA plus d lambda A dt. And also we can have for phase B, phase C, and also the rotor field winding. Here, for rotor field winding, the relationship I'm writing after the transient, because when the machine starts, right, there's still the transient. So, and also when the machine really is functioning, even if we said steady state, rigorously, the field winding is not exactly DC, it's very close to DC, not exactly. So anyway, we just write down the transient relationships. When we have A plus IB plus IC is equal to 0, so when this happens, we have the relationship between the flux and current. So my lambda A, lambda B, lambda C, lambda F, I put them together as a vector. And here, that's IA, IB, IC, IF as a vector. Then this inductance matrix will describe their relationship. And for round rotor machine, this part is a diagonal matrix. Now, this part just describes the mutual coupling between stator and rotor. Now here is the self-inductance of the rotor. So the next, we just see the equation for phase A voltage. So V sub A is equal to R SIA plus d lambda A dt. Then lambda A is equal to L sub S IA plus LSF cosine theta omega E IF. So that's here. Now at steady state, we have d theta ME dt is equal to omega E. Omega E is the electrical frequency. So then from this relationship we have theta sub ME is equal to omega E T plus phi R. Phi R is just a constant which describes the phase of the rotor. Then we can just put this relationship into here. So we have V sub A is equal to R SIA plus LS DIA dt. So we do the derivatives. The LS DIA dt, then minus LSF. Then at steady state, this IF becomes DC IF. Then we do the derivative, d cosine omega theta omega E dt. So this d cosine theta omega E dt will give us omega E sine omega Et plus phi R. And also there's a negative sign here. Now this V sub A, go ahead, we can write down this one as a real part of this complex function. Now after that, we can do this. We can describe this V sub A in terms of the phasor. So we assume the phasor for V sub A is this boldface V sub phi, V phi, e to the j omega et. So VA is equal to the real part of this, and IA is equal to the real part, this one. Then we define this term as E sub A, E sub A. So then we can get the phasor representation. So that means this term will be here. So that means V phi will be RS and IA plus JXSIA plus EA. So because when we just do this operation d by dt will go to e to the j omega et. Then there will be an omega e coming out. Then omega e multiply ls we define as xs. So xs is equal to omega e multiply ls. Then this term becomes EA. So we have EA here. So we can get this relationship in phasor domain. So we have V sub C is equal to RS IA plus JXS IA plus EA. Then this one we can describe using a circuit. So this circuit V phi is equal to EA plus JXS IA plus RS IA. So that's what we can get for the round rotor motor. Now the next. So how about the generator? Now for the generator, we switch the direction of the armature current. But the direction of the field current we don't switch, because at steady state is basically close to DC. So you don't, and also the rotor does not connect to the external circuit. So your field, the north pole still north pole, south pole still south pole. So the direction of field current we don't switch. So if we switch the direction of the armature current, then here we have to add a negative sign to the IA. Now even if I have these two figures, so this IA is actually negative of that value. So that's, even if I still mark IA, but their direction will be different. So for the terminal voltage relationship, I put a negative sign here. So also here we put negative sign here, negative sign here, negative sign here, but this one we don't change the sign. So we have lambda A is equal to LS negative IA, then plus LSF cosine theta ME IF. So we put a negative sign here, we can get lambda sub A. Now if we put this lambda sub A there, so we can just get to this relationship. So we still define the phasor, we will just get to here. So my E sub A is still this. Then that means for the generator, because the generator will provide electricity to the load. So that's why people use the notation with the current going out of the generator. Now the next, we look at this E sub A here. So what is this E sub A? Now from the generator we can see clearly, because if the generator connects to no load, that means just open circuit. The load is open circuit. But since the prime mover is still running, so we have the voltage the induced voltage of the EMF created, the E sub A will be created. Since you have no load connected, then this E sub A is just equal to V sub C when IA is equal to 0. So E sub A is called the open circuit voltage. So because the stator has no current, so that means there's no magnetic field created by the stator when the load is open circuit. Then the field of this case, when the load is open circuit, the field all comes from the rotor's magnetic field. So that means, so when it's open circuit, how can we calculate the flux? Well, we can just assume the field all comes from the rotor. So we will have this relationship. So the magnetic field in the air gap from the rotor field winding is equal to this BF peak, then cosine omega ET minus P over 2 theta A plus a phase. Then because cosine A is equal to cosine negative A, so we can just add a negative sign. We put P over 2 theta A at first, and minus omega ET minus Cr. Now, this magnetic field will go into the stator winding. When it goes into stator phase A winding, it will create a flux in phase A winding. So I developed a formula. So that's just basically my formula. So that's N sub A hat Vf peak cosine beta. So here beta is this. That's negative omega ET plus Vr. So we will just get here. Then this phi is here. That's just the flux of one turn. Then multiply the effective number of series turns, N sub A hat. So we will get this lambda sub A. Then the open circuit voltage will be E sub A d lambda A dt. So we will just do the derivative on this. Then we will get, so we can look at the derivative here. That's just the omega E sine omega ET plus Vr, and because it's derivative on cosine, so we need to add a negative sign here. Then we can also have this, just NA hat, this, then df peak dt. I'm sorry, no, there's no omega E here. At steady state, this magnitude is a constant, so we have d phi dt is equal to 0 at steady state. So this term we can take out. And for when it's transient, we still need to have this term. But now at we are looking at steady state, so this is 0. Then my E sub AT is just this term, just this term. So we can change its sign to be cosine. Then we can write down, because once it's cosine, that's just the real part, e to the j omega et plus Vr plus pi over 2. So then the phasor would be NA hat Vf peak omega e to the j Vr plus pi over 2. So that's the phasor. So we say that's E sub A is the open circuit voltage. So here is the derivation from just the physics. So when it is open circuit on the stator, the magnetic field only comes from the rotor. Then we finish this derivation, we get this E sub A. Now we also got E sub A here through the mutual coupling, right? So we just define this term as E sub A. Then can they be consistent with each other? The answer is yes. So this one is from the mutual coupling. L sub SF we got before. Now here is what we got from this. Then this BR peak for the rotor's field, we have this. So we can plug in here, right? Then put this one there. And here we just put this one there. Then we can get, actually, they are exactly the same. So this E sub A, we find as omega E, this E to the J phi r plus pi over 2. No matter we using this derivation or that derivation, we get the same thing. Then we can just define this term as lambda f peak. Actually, this lambda f peak, just this term. This term we define as lambda f peak. Then this E sub A is equal to omega E lambda f peak e to the j phi r plus pi over 2. Then on the RMS, we have to multiply 1 over square root of 2. So the E sub A RMS value, we do this. We use 1 over square root of 2 multiply here. Or this part just becomes this. Okay? Now we look at here. So E sub A RMS. So this N sub A F phi F peak, this one is just my lambda F peak. So square root of 2 multiplied pi is about 4.44. So actually here is 1 over square root of 2 multiply omega E, right? Omega E is equal to 2 pi Fe. Then we get square root of 2 pi. So that's approximately 4.44. Now we can move this F sub E to the left hand side on the denominator. So that means E sub A over F sub E is equal to this. So when the machine is built and also when the field current is specified, this will be a constant. So when this is a constant, if we have a 60 Hertz generator, if this 60 Hertz generator, then we can get this E sub A for 60 Hertz. Now if we want this generator to work at 50 Hertz, then this E sub A value will change. How much will change? It actually becomes 50 over 60. So it has to be derated. The E sub A, when 60 Hertz, we get something, and 50 Hertz, let's say 60 Hertz we get 60 watts. 50 Hertz will get 50 watts. So that's the need. Now, the induced phase voltage. So, for the net magnetic field, so if the rotor's magnetic field and stator's magnetic field, they add up together, that will become the net magnetic field. So that means my stator will have current. Then the stator's current will create stator's magnetic field. We add up them together, we have the net magnetic field. The net magnetic field will create the terminal voltage or the phase voltage. So V sub phi will be from the net magnetic field. So if we have the net magnetic field, we can get the flux in phase A winding from the net magnetic field. I don't need to do the derivation again. It will be very close, to here. So the result will be FA net is equal to NA hat phi peak cosine omega ET plus phi net. And phi peak is equal to 2B peak dl over P. So this one is also the net. Then d lambda A dt will give us V phi. So because at steady state we assume d phi peak dt is equal to 0, then we just get this. So we can also describe V phi in terms of the phasor. Then we can also get RMS voltage for the phase voltage, right? So we can get RMS phase voltage, so which is here. This formula is just like this one, so we just change this one to be the flux from the net magnetic field. Then we can also connect the generator winding. So we can have Y connection. So this part is the generator's equivalent circuit. Now this figure shows how we can connect these three phases in Y connection. Now we can also connect in delta connection. Now I only draw the connection for generator. For motor, you just switch the current direction. The other things are the same as the generator case. Now here we have two examples. My example 1, for 3-phase 4-pole 24-slot 5/6 pitch machine with double layer lap winding, the peak magnetic field intensity in the air gap is equal to 0.45 Tesla. There's one slot skew. The machine shaft speed is given. The stator inner diameter, the machine lengths are all given. So there are 10 turns per coil. All the turns are connected in series. So what's the RMS phase voltage of the machine? What's the RMS terminal voltage of the machine? Because it's connected in Y, I need to specify it should be connected in Y. So if we get the phase voltage, if connected in Y, then you know how to get there. So you have to use square root 3 multiply the phase voltage. But for the phase voltage, we just follow this formula. So when we use this formula, we have to calculate NA hat. So we have to calculate NA hat. So NA hat is equal to NA multiply KW. NA we can calculate pretty straightforward. Then this KW is equal to KD multiply KP multiply KS. So we can just use the formula we obtained to do that. So this one is a double layer lap winding. Then example 2. So example 2, we just have a very simple machine, and also it has a single layer winding, only one full pitch coil. Now this case, because that's just only one coil, so this NA hat is just simply equal to N sub C. This is a single layer winding. No distribution, right? No fractional pitch, it's full pitch. No skew. So KW is simply 1. So this NA hat is equal to N sub C. Only one coil. So the number of turns for this coil is just equal to NA hat. This B peak is given. So we can go straight forward, plug in, and get the result. Now the next. the voltage and speed regulation of the machine. So if the machine is a generator, we need to look at the voltage regulation. So the voltage regulation is simply defined as the no load voltage minus the full load voltage over the full load voltage multiplied 100%. Now if the machine is a motor, so we need to look at the speed regulation. So the speed regulation of the machine is equal to the no load speed minus the full load speed over the full load speed multiply 100%. Or you can use N, which is RPM. The unit is RPM. So no load, right? Speed minus the full load speed over the full load speed multiply 100%. So this time the load means the mechanical load for speed regulation. So if you just have a machine, you don't connect to anything, that's just no load. When you use a machine to do some work, right, then you apply for load. For generator, the load will be the electrical load, not the mechanical load. Here, for motor, that's the mechanical load rather than the electrical load. Now for a machine, we will also have the efficiency. So the efficiency will be the output power over the input power multiplied 100%. Then the output power is equal to the input power minus the loss. So this is true for both generator and motor. For generator, P out is the electrical power. P in is the mechanical power. Mechanical input power from the shaft, from the prime mover. For motor, P out is the mechanical power. Then P in is the electrical power. Now we look at the AC machine loss mechanism. So typically for a machine, no matter it's a generator or a motor, the most important loss, I would say, is the electrical loss or copper loss. That means the windings will have a current goes in, right? No matter you have stator winding or rotor field winding. Then I square R is the loss. That's the copper loss. The second would be the core loss. Core loss also has two parts, the hysteresis loss and the eddy current loss. Then the third part of the loss is the mechanical losses. So mechanical losses will basically, we will have friction loss and windage loss. So the friction loss mainly caused by the friction of the bearings, and the windage loss will be basically caused by the friction between the moving parts of the machine and the air inside the motor or generators. AC. So that's basically the friction loss and the windage loss will contribute to the mechanical losses. And there are also stray or miscellaneous losses. The stray or miscellaneous losses will just be some loss which we cannot put in those three categories. So also some factors, which is difficult to say exactly what it comes from. So you add up all the copper loss, you add up all the core loss, add up all the mechanical loss. There's still something left over. So those losses we just call stray loss or miscellaneous loss. So those may take, just about a little part, maybe, just 1%, only a little part. Now here this slide shows the copper loss, right? The first item, the copper loss. So we may have stator copper loss, P sub SCL, because it's three phase, so 3 IA squared RA. Now all R sub S. In my notation, I change R sub A to R sub S, more frequently. But sometimes I still use R sub A. If you find in my notes you have R sub A or R sub S, they're the same. Then the rotor copper loss will be I squared F RF. So that's for the loss mechanism. Then we look at the AC generator power flow. So for generator, the input will be the electrical power. So the electrical power, there will be an applied torque multiply the mechanical speed omega sub m. That's the input, right? So then we will have maybe some stray loss, mechanical loss, core loss. Then we get up to here. So this one is a torque from, people call it induced torque or call it the kind of electromagnetic torque. So up to here, this torque comes from the interaction of the current and magnetic field in the machine. So that's why I mark as T sub EM. T sub EM multiply omega sub m. That's the power converted from mechanical power to electrical power. So that's here. Then once you have this power will have include the I square R loss and the output power. So the winding, copper winding will take some out of this P conversion. Then the rest will become the output electrical power. So the output electrical power, if three-phase machine, we can describe either using, the first one, right? That's the phase voltage and phase current, or use a line voltage and line current. No matter it's Y connection or delta connection, they're all correct. Now the motor. So for motor, the input power will be the electric power. So we have the electric input power there. Then there is I square R loss. Now after that, the power will be converted, right? So that the converted power is equal to the electromagnetic torque multiply omega m. And this, after this conversion, we will have core loss, mechanical loss, stray loss, then become the output mechanical power. So the output mechanical power is just equal to T load multiply omega sub m.